All right, everyone, let's start talking about pH. Now, pH is going to be very important because it's going to factor into how enzymes work, how proteins work. So your body's going to be really focused on regulating pH levels. So when we talk about acids and bases, really they're simply electrolytes. And I know you guys have heard that term. It comes up all the time when we talk about, Gatorade and all that kind of thing. But basically an electrolyte is anything that releases ions in water. So technically an acid and a base is simply an electrolyte. An acid is a specific kind. It releases hydrogen ions. A base dissociates hydroxide ions, so it releases hydroxide ions. That's sort of the difference. Now, salts are electrolytes that simply release ions, and neither of those ions can be hydrogen or hydroxide. Those are your definitions. Okay. When we talk about pH, what we're going to be focusing in on are the concentration of hydrogen ions in the solution. Okay, so we're going to be talking about how much, what is the concentration? How many of these hydrogen ions do we actually have in solution? All right, and our pH ranges from 0 to 14. There is no 15, there's no -1, it's 0 to 14. That's it. So if you take a look at this graph, that's what I want to bring your attention to. So here in red, we have hydrogen ion concentration. That's what those brackets mean, okay? So here you can see on the left-hand side, there's a lot of red. And then what you have here are hydroxide ions represented in blue. So you can see here, again, on the left-hand side, lots of hydrogen, very little hydroxide. pH down here is of 0. Okay. So as we go toward the right, and let me actually hide my image for a quick second. When we go here toward the right, you'll notice that the red becomes smaller and smaller and smaller. So what this means is that we have fewer and fewer hydrogen ions. Conversely, we have more and more hydroxide ions. Okay? So what we have here is, again, so just very simply, the more hydrogen ions we have, the more acidic something is going to be, our liquid's going to be. The fewer hydrogen ions we have, the less acidic or more basic or more alkaline the solution is going to be. Okay, it's just that simple. So our numbers here are basically 0 is going to be the most acidic, 14 is going to be the most basic or the least acidic. It's either thing's the same. And then right in the middle, what you see here at neutral, if you look, there's the same amount of red as there is blue, so there's the same amount of hydrogen as there's hydroxide, so it's neutral. Okay, basically the two cancel one another out. It's neither acidic nor is it basic. It's basically neutral. It's somewhere in the middle. It has no charge, if you will. It's not necessarily charged, but it has no acidity, no alkalinity. It's neutral. Okay. When we talk about pH, we say that it's on a logarithmic scale. Now, I don't want to scare you with math and stuff like that, but it's actually very, very simple. All this means is, so let's just go from, I don't know, from this neutral, from this where it's neither acidic nor is it basic, and let's go toward basic. Okay, so if we go this way, so if we go from something that has a pH of 7 to something that has a pH of 8, it's not just whatever that difference is, not just 1 times different, it is actually 10 times more basic. Okay, so something that has a pH of 8 is actually 10 times more basic than something that has a pH of 7. Okay, and if I went from 8 to 9, again, that is 10 times more basic. Okay, so each number, there's actually a tenfold difference between each number. This means that if I went from 7 and skipped 8 and went straight to 9, the difference between 7 and 9 is not twice or whatever that amount is, 1.5 times. It's actually 10 times 10, so it's actually 100 times of a difference. So something that has a pH of 9 is 100 times more basic than something that has a pH of 7. Okay, hopefully that makes sense to you. And that goes either way. So we can actually say if we're going this way from 7 down to 6, again, that is a 10-fold difference. Okay, and in this case, since we're going to the left on this graph, now we're becoming more acidic. So something that has a pH of 6 is 10 times more acidic than something that has a pH of 7. Similarly, you go from 6 to 5, that also is going to be a 10-fold difference. So again, something that has a pH of 5 is 10 times more acidic than something that has a pH of 6. And again, if we go from 7 to 5, it is a 100-fold difference. So something that has a pH of 5 is 100 times more acidic than something that has a pH of 7. And you can do this all the way down, the length of this graph. Okay, so that's just what you're seeing here is a summary of everything that I just said to you moments ago. Again, in our bodies, we're going to care about our biochemical reactions. They're going to be very sensitive. If we have a pH that's too high or too low, things will not function correctly, and you can have real problems. Like you can have nerve damage, you can have convulsions, you can fall into a coma, you can even die. So it's your body's going to be regulating these pH levels very closely. Now here are just some examples on this slide of things in our lives that and where they sort of fall on this range. You do not need to worry about memorizing these for an exam. I just wanted to give you an idea of where these things are. So again, distilled water, you can see is at that nice neutral. Our blood is actually a little bit more basic than neutral. You can sort of see where black coffee is. And if you take a look, I don't know if this is surprising to you or not, but soft drinks have a very acidic pH, and that's universal all soft drinks. So even something that's very sweet, like, I don't know, I take 7-Up to be something that's very sweet, or 7-Up or Sprite. If you use a pH strip and you measure its pH, it is fairly acidic. I mean, that's not that far away from gastric juice, really. Okay. So anyway, just kind of thought you might like to know, give you an idea of where some of our things in our lives falls on this scale. One of the things that's going to maintain pH in our bodies is going to be this equation right here. And you're going to see this come up over and over and over again. This is a super important equation in biology, in all of biology, not just anatomy and physiology, but even out there biology. This equation explains how acid rain happens. You've probably heard of ocean acidification in other classes or in the news. This equation explains how and why that happens. So simply put, you take carbon dioxide, and if you mix it with water, it forms something called carbonic acid. So this is carbonic acid. Okay, that's carbonic acid. That carbonic acid is going to quickly dissociate into hydrogen ions and bicarbonate. Okay, so this is bicarbonate. That means that the more carbon dioxide you have, okay, so the more this carbon dioxide you have, the more hydrogen ions you're going to have. What we just saw was the more hydrogen ions you have, the more acidic something is. So again, by putting a lot of carbon dioxide into our atmosphere, what's going to end up happening is that we're also, it's going to mix with water, so like in our oceans and stuff like that, which then causes this reaction to occur, and it forms hydrogen ions. It turns the water acidic. This is how you get acid rain, particularly in cities where there's a lot of pollution. Okay, your body's gonna be very good at this. This is also what happens like if you hold your breath. So if you hold your breath too long, you're going to increase carbon dioxide levels, and what ends up happening is your blood actually starts becoming more acidic. You have sensors in your body that pick up on this, and if you don't do anything about it, like if you don't basically start breathing again, right? Like you usually, you know what I'm talking about. Like if you hold your breath for a while, after a bit, you start getting that real sense of urgency, like, oh my God, I got to take a breath. Like I can't, you almost start getting panicked, right? But if you still refuse, you'll pass out. And basically what will end up happening is that your lower brainstem will take over your breathing for you. Similarly, this equation is going to explain why if you hyperventilate, you also pass out. So basically when you're hyperventilating, you're decreasing your carbon dioxide levels because basically you're breathing them out, which means that you're pulling these hydrogen ions out of solution and you're breathing them out in your breath, and breath out. So basically by losing hydrogen ions, right? Remember we saw in that graph just moments ago, the fewer hydrogen ions we had, the more basic something became. So similarly, if you're hyperventilating, like you're stressed out, you're hyperventilating, again, you're going to pass out because you have sensors in your blood that are saying, whoa, 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 our blood's becoming way too basic. What's going on? Something's happening. We're going to pass out. We're going to have the lower brainstem take over, and they're going to help regulate this breathing because apparently whatever we're doing, that's not the right answer. So let me know if you have any questions on pH or if this didn't make sense to you. Feel free to email me about this. I'm more than happy to go over this with you guys. There are some quiz questions on this. Again, before you take the quiz, if you have any questions, again, feel free to email me. All right, there's just a few more things and then we'll finish up this chapter. One of the things is, just want to bring your attention to chemical reactions. So we have basically what we're talking about are reactants. They're going to interact and then you end up with products, right? So you can see here we have hydrogen ions, oxygen molecules. They're going to come together. You end up having products, which is water, right? And by the way, just something going back a quick second, on this equation, you'll notice that these arrows are going in both directions. That means that this is a reversible reaction. And what that means is that it can go toward the right and it can also go toward the left. Not all equations are like that. Many of them, once you have products, they cannot go back to the reactants. This can. They can go from one direction back to the other. It's not like there's no end point really. It can go back and forth. We're going to talk a little bit about enzymes this semester, particularly when we start getting into the muscular and nervous system. You'll end up talking a lot more about them in 202. You're going to hear a lot of enzymes in 202, particularly when you talk about the digestive system. But basically what an enzyme is, it's a protein that helps speed up chemical reactions. Okay, that's basically what it is. And you can see here, it helps it speed up a lot. That's not even a made-up number, although it kind of seems like it would be 10 billion times faster. Okay, and enzymes are unchanged after this reaction occurs. So once it breaks one of whatever down, it can go and break another one down, and another one down, and another one down, right? And you can tell when something's an enzyme because it ends in ASE. And whatever comes before the ASE is what it's breaking down. Okay, so protease breaks down proteins. Lipase breaks down lipids. So sucrase breaks down sucrose. Okay, so pay attention to that. It'll make your life so much easier as you're going forward, because a lot of times you're going to see something that ends in ASE, it's a long word, and you're going to be like, what does it break down? Well, whatever comes before it, it tells you. There's very few exceptions to that rule, so just remember that rule of thumb. You'll thank me for that later. And that's it. Again, email me if you have any questions. Don't forget to take the quiz.